The second thing we're going to do today, first thing being construct and interpret confidence intervals. The second thing is find the sample size. If you are conducting a survey and you want your survey to be taken seriously by somebody, then you have to survey the appropriate number of people. 2 is not an appropriate number of people to survey no matter what you're trying to prove. That's a darn small sample. But depending on what you're surveying, the purpose of your surveying, and how confident you want to be in your survey, you may have to only interview 100 people. But if you want to be really, really, really confident, you may have to interview 1,000 people. How do you know how many people or how many whatevers need to be included in your survey? There's a formula for that. There's no button for that. We're actually going to have to work with a formula that's scary looking but not hard to work with. Suppose we want to collect sample data in order to estimate some population proportion. The question is, how many sample items must be obtained? Here are 2 formulas. If we know the sample proportion, when the sample proportion is known, you use this formula. If you don't know the sample proportion, you use the second formula. But we have to figure out what all these things stand for. We already know that p hat is the sample proportion who do something, do believe, do whatever. Guess what q hat is? The proportion who doesn't. So these 2 numbers always have to add together to give you 1. In the previous example, if p hat was 0.7, then q hat would be 0.3. But if you don't know p hat, then you can't find q hat. You're going to have to use 0.25. That 0.25 is coming from, if I don't know p hat, let's just say there's a 50-50% chance of success, or a 1/2. The odds of success are 1/2. What's this 1/2 times 1/2? 1/4. That's where the 0.25 is coming from. You have to use that if you don't know the sample proportion. So we've talked about p hat. We've talked about q hat. We have to figure out what this z sub alpha over 2 is. And we have to figure out what this e is. Next couple slides are trying to explain what the z sub alpha over 2 is. In Chapter 6, we talked about critical values. And even while we were talking about them, I said, we're going to mention these now, but they're not going to be important in Chapter 6. They're going to be very important in Chapter 7. Here's where they become important. Z sub alpha is the z-score with an area of alpha to its right. In other words, for some normal distribution, there's some z sub alpha, and that alpha is the area to the right of that z-score, or the probability that an individual value falls to the right of that z-score. However, when we used inverse norm to find a z-score, what did we always have to type in to the argument for inverse norm? The area to the left. Z sub alpha, alpha is the area to the right. What would be the area to the left? The complement of it, 1 minus alpha. And that's why in Chapter 6 we had a problem that said find z sub 0.02. We didn't type in inverse norm 0.02. We typed in inverse norm 0.98. The alpha is giving you the area to the right. So 1 minus alpha is the area to the left. And that's what you have to type in for inverse norm. For example, if alpha is 0.05. To find the z-score that has a probability of 0.05 to the right, you have to punch on the calculator z or inverse norm 0.95 instead of 0.05. But this is not z sub alpha that we're talking about. That formula had z sub alpha over 2. Remember, it wasn't just z sub alpha, it was z sub alpha over 2. Let's talk about this without understanding why, and then until the next slide. Here's what's going to happen. I'm going to give you some confidence level. Alpha is 0.05. For reasons that you don't understand yet, you're going to take a half of that. A half of 0.05 is 0.025. So alpha over 2 is going to be the area to the right, and 1 minus alpha over 2 is going to be the area in the middle. So we're going to type in inverse norm 1 minus 0.025, or 1 minus 0.025 is just 0.975. When I type in inverse norm 0.975, I get a critical value of 1.96. That's a z-score. That's a z-score that has 2.5% to the right of positive 1.96, and we're fixing to find out on the next slide, 2.5% of the values falling below negative 1.96 to the left. That's why you divide by 2. We're not just concerned with this tail end, but also that tail end. All right. Think really hard here. You don't have to write anything. I've typed everything. To find a z-score associated with a probability of alpha over 2 falling in the right tail. Actually, let me show you the next slide, which gives you a specific example, and then come back to this general. I think the general is easier to understand if you find the specific first. Remember what this is all leading up to, because right now, if I'm feeling kind of swamped and confused, I multiply that by 1,000, and that might be how you're feeling right now. What the crap? I get it. I know that's what you're thinking. This is not hard to do if I can make the light bulb come on. It's an easy formula. Just talking about what all to plug into the formula is a little bit of a nuisance. Once you get the hang of that, the formula is easy to work with. All right, so here's what a problem is going to look like. In the homework, you're going to have a problem that says, what sample size must be polled or must be experimented with or whatever in order to be 95% confident, to have a 95% confidence interval. The question is, how many people do I have to survey? First thing you're going to think is, ooh, there's a formula for that. Second thing you're going to think is, and I have it written down on my index card. Okay? Then you're going to look at that index card and you're going to say, oh yeah, I have to find z sub alpha over 2 to plug into that formula. Well, I just said I wanted to be 95% confident, so what is alpha? 0.05. What is that divided by 2? 0.025. So to find the z-score that has 2.5% of values to its right, I have to use inverse norm. But to use inverse norm, I have to find the corresponding area to the left. If 0.025 is to the right, then 1 minus 0.025 is to the left. If you can't do it in your head, you actually can type in 1 minus 0.025, and the calculator will, yes, sir. Yeah, sure. Charlie. Okay. So 1 minus 0.025 gives us the area to type in, the area that we have to type in to the left of the z-score that we're looking for. We enter inverse norm 1 minus 0.025 and find that z-score to be 1.96. That 1.96 is the z-score for which 2.5% of the population is to the right of that, and 2.5% of the population is to the left of negative that, because of the symmetry of the normal distribution. If we want our confidence level to be 95%, then there has to be 5% outside that, 2.5 to the right, 2.5 to the left. And that's why we find z sub alpha over 2 to plug into that formula. 1.96 is the first number that we would enter into that formula. Now going back to the general slide, this was a specific confidence level of 95%, but in general, for any confidence level, you tell me a confidence level of 90%, I'm going to say alpha is what? 10% or 0.10. So alpha over 2 would be 0.05, and 1 minus 0.05 is 0.95. So z sub alpha over 2 would be inverse norm 0.95. Take half of the confidence level, subtract it from 1, then use inverse norm to get that z-score that you type into the formula. The formula had a z sub alpha over 2. It had a p hat and a q hat, and we already know what those stand for. The only other thing in the formula was that e in the denominator. What was that e in the denominator? It's called the margin of error. When you hear all of, yes, ma'am. Yes. And so z sub alpha over 2 is 1.96, but when we put it into the formula, we'll square it. Yeah. We're just trying to make sure you understand where all the numbers that go into the formula come from, and then how do you punch it on the calculator to find the sample size. So the only thing we haven't talked about is that e that's in the denominator, and that's called the margin of error. I am almost certain that if you have watched any news in the last year, you've heard poll predictions about Obama winning versus Romney winning. I don't know what the current numbers are, but it appears to be the closest race in the past several decades. You might hear that the percentage of people expected to, I'm just making numbers up here, expected to vote for Obama is 53% or 0.53. What you will always hear or see right after that is plus or minus 3 percentage points or plus or minus 2 percentage points. The statisticians, the media are giving us their level of confidence. It's either, if I say the percent of people voting for Obama is 0.53 plus or minus 3%, that means I think that either somewhere between 50 and 56% are going to vote for Obama. So E is that acceptable amount of error that somebody decides. If you say, how many adults must be surveyed in order to be 95% confident that the population proportion is in error by no more than 3%? Then I'm going to use E as 0.03 because that's 3% written as a decimal. Now we know how to find Z sub alpha over 2. We have to be given P hat. We know how to find Q hat. We know how to find E. We have all the elements of that formula. Let's put it all together. And round, up to the next whole number. Folks will miss this problem on the test simply for not rounding correctly, because on every other problem you're told round to the nearest tenth or round to the nearest hundredth. You can't poll a half a person, right? We're looking for number of people to poll. We've got to have a whole number. But we're not going to round to the nearest whole number. What if my number turns out to be 51.1? 51.1 is the number of people I have to survey in order to be 95% confident of blah, blah, blah. If I only poll 51 people, am I going to be 95% confident? It has to be at least 51.1. So rounding down to 51 is going to make me maybe only 94.9% confident. If I want to be at least 95%, then I'm going to have to round up to the next whole number. No matter what is in the tenths place, round up to the next whole person, because we can't interview a half a person or a third of a person. Okay, let's do a couple of examples using the sample size formulas. The key to knowing when you need to use these formulas, if the problem says how many, that indicates sample size. If it says how many must be surveyed in order to be confident about a percentage, then that's one of your sample size formulas for proportions. In the next section, we're going to have sample size formulas for the mean as well. With this example, the internet is affecting us all in many different ways, so there are many reasons for estimating the proportions of adults who use it. Assume that a manager for eBay wants to determine the current percentage of U.S. adults who now use the internet. How many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? The fact that it says how many tells us to use one of our sample size formulas. All of our sample size formulas, we're going to have 3 of them, but they all begin in equals. And the fact that we're estimating a percentage or proportion here tells us to use one of the 2 formulas that I gave you a couple of slides ago. We'll go back to that in just a second. The A part says in 2006, 73% of adults use the internet. That's our proportion from the sample. Our p hat is 0.73, which means our q hat is 0.27, 1 minus 0.73. So in the A part, we know a p hat. In the B part, it says no known possible value of the proportion. That means that I need to use the second formula for when I don't know p hat. All right, in the A part, I know the sample proportion is 0.73. I know the complement of that is 1 minus 0.73 or 0.27. I was asked to use a 95% confidence level. That means that alpha is 0.05. And the problem said sample percentage is in error by no more than 3 percentage points. That's giving me E. And these are the values that I need to substitute into the formula. The formula is Z sub alpha over 2. For a 95% confidence level, that means alpha is 0.05. I find Z sub alpha over 2 by using inverse norm. But to find the critical value, Z sub alpha over 2, I don't enter inverse norm 0.05. I enter inverse norm 1 minus 0.05 divided by 2. That's my alpha, and that's divided by 2. Now, if I use inverse norm 1 minus 0.05 divided by 2, I get approximately this value on my calculator. If I use a rounded value for that, if I use 1.96, for example, some of the times I'm going to get the right answer, but some of the times I'm going to get the wrong answer because I'm using an approximated value for that critical value. In math, you never round in the middle of a problem. So instead of rounding that 1.9599 to 1.96, I'm going to either use the whole value, write it all down and type it back in. That's the slow way. Or I'm going to type inverse norm 1 minus 0.05 divided by 2 equals, and then continue the formula without writing that number down. When I type inverse norm 1 minus 0.05 divided by 2 equals, this entire number shows up on my calculator, but rather than rounding it or writing it down and typing it all back in, I'm just going to keep going and square that number. And then multiply it by my p hat, multiply it by my q hat, and divide by the value of e squared, because that's what's in the formula, divide by e squared. So divide by 0.03 and then the square button and then hit equals again. Let me show you exactly what that looks like on the calculator, because this does take just a little practice entering on the calculator. Inverse norm is under my distribution menu, so second and VAERS and number 3 pulls up inverse norm. And then I want to enter 1 minus my alpha. For a 95% confidence level, my alpha is 0.05 divided by 2. That's 1 minus alpha divided by 2, and that's the 1.9599 that I don't want to round. I want to leave that on my calculator and just continue with the formula. When I press the square button, the calculator will square my previous answer. So it's not rounding and squaring, it's keeping up with all those digits, which gives me a more precise answer. My answer squared times the p hat was 0.73 times the q hat is 0.27 divided by my e 0.03 squared, and then equals, and I get an approximate value of 841.3. But remember our rounding rule for the sample size formulas. If I only interview 841 people, I'm going to be a little bit shy of my 95% confidence level. So no matter what is in the tenths place, when I use one of these sample size formulas, I'm always going to round up to the next integer to make sure that I achieve the amount of confidence that I wanted to have. To be 95% confident that our sample percentage is within 3 percentage points of the true percentage for all adults, we should obtain a simple random sample of 842 adults. All right, the B part uses mostly the same information, but in the B part, I didn't know this p hat. So rather than using the formula that had p hat and q hat in it, I need to use the formula z sub alpha over 2 squared times 0.25 divided by e squared. I find the z sub alpha over 2 the same way that I did on the previous example, but instead of p hat times q hat, the formula just has 0.25 and then divide by the same margin of error squared. So on the calculator, that's second distribution menu, number 3, to pull up inverse norm and say 1 minus alpha over 2 gives me the 1.95 that I'm not going to round. And then just keep going with the formula. Square that, multiply it by 0.25, divide by the margin of error squared, and I get a much bigger sample size is required when I don't start with a sample proportion. If I'm just guessing at the sample proportion, I'm going to have to use a larger sample. So that on the calculator is approximately 1067.1. But again, regardless of what digit is in the tens place, I'm going to have to round that up to achieve the confidence level that I want. To be 95% confident that our sample percentage is within 3 percentage points of the true percentage for all adults, I need to obtain a simple random sample of 1,068 adults. All right, that concludes this section, which had confidence intervals for proportions and sample sizes for estimating proportions when we knew a sample proportion and when we did not know a sample proportion. In the next section, we'll do the same thing for means. Have a good day.